In this question, we've got three counting or almost probability problems, but they're really just counting or permutation and combination problems. So these are sort of shortcut ways of counting big numbers or the number of ways that things can happen, and this sort of acts as the basis of probability. So let's look at the first thing. How many ways can 9 people be arranged in a row? Okay, so let's imagine you've got your 9 people sort of standing off to the side, and you've got these 9 seats. So I'm going to draw the seats as like slots here almost. 5, 6, 7, 8, 9. So there's 9 places for people to go in a row. And we want to basically know how many different arrangements are there. So as you move 2 people around, that's a new arrangement. So you've got sort of, again, imagine your 9 people are just hanging over in this room. There's 9 people, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each dot is a person. 9 of them hanging around. We've got to fill this first spot first, or we can fill any spot. Let's actually say we want to fill the middle spot first. And there's no restrictions here, so let's start with the far left spot. I want to fill this far left spot. How many ways can I do that? I can do that 9 different ways because there's 9 people I can choose from. Now I've chosen one of those people, right? One of them is here now. How many ways can I fill the second spot? 8 people. How many ways can I fill the third? 7 people. 6, and it keeps going down by 1 because you're taking one more person out and filling it there. So by putting a 9 here, that represents the number of ways we can fill that first spot. Even though there's only going to be one person there, it can be any one of those 9. So you have to think about it that counts for 9 different arrangements. We're going to multiply each of these together. It's going to be 5, 4, 3, 2, and at this point, there's only one person left from the group who has them in place. There's only one way to fill this last spot. You multiply all those together because of the word and. We can fill the first spot with 9 people, and the second spot with 8, and the third with 7. In probability or counting problems, whenever we use the word and, that represents multiplication. So another way of writing this is 9 factorial. That factorial or exclamation sign on the end usually doesn't belong in math, but when we have it, it means go from 9 and multiply every digit to it down to 1. So you can just pop this in your calculator or do the whole thing manually, and we get 362,880. So that's how many ways, unrestricted, that we can arrange 9 people in a row, which is pretty crazy. It's a super high number. And kind of thinking logically about that again, if we have 9 people, how many different ways can we rearrange them? Well, even just changing 2 of those people counts as 2 different permutations. So you can imagine what happens as you move all 9 of them around. Let's look at number 2. How many ways can 9 people be arranged in a row if Bob and Sally must sit next to each other? So this is the same question. This is the same 9 people, except for now let's imagine these 2 are Bob and Sally. The way we do this is they have to sit next to each other. So now we're really only arranging 8 different people because we want to think of them as one. They have to be together. So how many ways can you arrange 8 things in a row? It's 8 factorial. Okay, that's pretty easy. But we have to adjust slightly because we're just counting this sort of red circle. Even though it has 2 people in it, we're counting it as 1. The one extra change we can make on that is switching them around within that group of 2. How many ways can you switch 2 people around? 2 factorial ways. So it's 8 factorial ways to arrange the 8 things in a row, and then multiply that by 2 because each time you switch Bob and Sally within their small group of 2, that counts as a new permutation. So again, you can pop this in your calculator, and we get 80,640 ways. And we would expect this to be less than this one here because there's a restriction on it, right? If Bob and Sally have to sit together, that sort of takes care of 2 people within 1. So you can see it's about it's about over 4 times less as many ways than the previous example. So that's the trick with groups of 2. Is group them together, count them as one thing, and then arrange them within that one group. For number 3, how many different 5-card poker hands are possible? So let's think about poker hands. You're choosing from 52 cards, and we've got to choose 5 cards. Now, does order matter here? What does order mattering mean? Well, if you get dealt let's just use a royal flush as an example. Ace, king, queen, jack, and 10 of hearts. It doesn't matter which order you get it in, right? It doesn't matter if you get ace, king, queen, jack, 10, or ace, 10, jack, queen, king, right? You're going to end up with a 5-card hand, and we don't count that any differently. We never care what order things come in. When order doesn't matter like that, we use combinations, or the letter C in our notation. Okay, so we're choosing from 52. We want to choose 5 cards. Any 5 cards, right? Because we're just looking for the number of different 5-card hands. This is obviously going to get popped into the calculator because it's going to be a very big number. And it is about 2.6 million. 2,598,690 hands. Right? So any given hand that you end up with, there is a 1 in 2.6 million chance that you were going to get that 5-card hand, which is really crazy, which is why cards are such great instruments for teaching probability and counting, because there's so many different permutations. Again, combinations when order does not matter. A good example there is picking 6 people from a group of 8, just picking them. But when would we use permutations? When order does matter. So if you had to choose 3 people from a group of 8 to place them in, say, president, vice president, or secretary, right? So the committee example with specific positions, that's a very good example for using permutations as opposed to combinations.